Today's lesson is on gas volume stoichiometry. So we're going to be expanding on what we learned last time with including masses in our stoichiometric calculations. And we're going to now, for gases only, be able to do some volume calculations. Meaning if I give you the volume of a gas, or if I ask for you to solve for what the volume of a gas from a chemical reaction would be, we're going to be able to practice doing that today. Now this is specific for gases under a certain condition called standard temperature and pressure. We will actually have an entire unit here in chemistry on gases where we will add a little bit more to our gas stoichiometry capabilities under conditions that are not standard. So that is something super fun for you guys to look forward to. But we're going to start off small and introduce this as another kind of an extension of our arms on our stoichiometry map. So for today, as always, we're going to need our pencil and calculator and hopefully a periodic table. I'm also using my red and my green markers to help me guide through my stoichiometry problems, as green indicating my go given and red indicating my end stop. Okay, so let's get started on gas stoichiometry. So remember, so important, all stoichiometry problems start with a balanced equation. If your equation is not written correctly, and if it is not balanced correctly, we know the mole ratio is not going to work out for you, right? Okay, so that is super duper important for us to really, lock in on that skill and get it where it needs to be. So this is where we kind of have started from. We started small with wondering what the mole ratio is and how it is useful for us to be able to, provided a given amount of moles of one substance in a chemical reaction, calculate the moles of another substance in the chemical reaction using the coefficients. So these x's right here represent the numbers that from the balanced chemical equation, the mole ratio. And then we extended it a little bit further where we're like, okay, how about I have the possibility of converting from grams to moles for my given substance, okay? Or I would have the possibility of converting from moles to grams of my ending substance. So we did this last time where I have a possibility of doing a 3-step conversion from grams of beginning to grams of end. But one thing to notice here is we have the mole ratio smack dab in the middle there, okay? That is where I cross the divided line. The divided line indicates where I stop talking about my guy and my chemical equation that I've given you information about, and I start talking about my guy and my chemical equation, where I'm asking you to give me information about, whether it be moles or grams, okay? So now let's see where are we going today with this. So the fun thing about gases, which is why I'm like super excited we have an entire unit on gases, because they are by far the most exciting state of matter in all of chemistry to study. No offense to liquids and solids, they can, enjoy their day too. But gases, we have an entire unit on them. So one cool thing about gases is if I have 1 mole of any gas at standard temperature and pressure, or I will abbreviate standard temperature and pressure as STP, okay? It will be equal to a volume of 22.4 liters. And that is actually very large, much larger than a normal balloon like the picture shows. But the interesting thing, you're like, well, what is so interesting about that? Well, this is actually really kind of cool. I don't care what the gas is. I don't care if it is oxygen gas. I don't care if it is nitrogen gas. I don't care if it is helium gas. I don't care if it is a big fat sulfur hexafluoride gas molecule. They're all going to take up the same amount of space. And if I have 1 mole of them, or 6.02 times 10 to the 23rd particles of them, it will occupy 22.4 liters. That is wild. I do not care how big or small the individual gas molecules are, okay? We know that a hydrogen guy would be very small compared to sulfur hexafluoride. That molecule is going to be larger. But because gases like to spread out and take up as much space as possible, the size of the individual molecule itself is basically negligible. Most of a gas is made up of the empty spaces between the molecules. That was a long tangent, but it's getting me hopefully pretty excited for when we talk about gases a couple of units from now. So that's wild. So the key thing here, which is going to be important leading up to our stoichiometry, is that 1 mole of any gas, as long as you are under these standard conditions of temperature and pressure, will have a volume of 22.4. So let's watch a video kind of expanding into that a little bit more.
Scientists have found that 1 mole of any gas occupies approximately 22.4 litres per mole under standard temperature and pressure. Standard temperature and pressure is 0 degrees centigrade and 0.986 atmospheres respectively. Scientists also quote molar gas volumes at 24 litres per mole, but this is at room temperature and pressure, which is 20 degrees centigrade and 1 atmosphere pressure. Can you think why the molar volume of a gas changes when it's measured at different temperatures and pressures? Pause, think, and continue when you're ready. In terms of temperature, the answer is that a gas expands when it's heated, so 1 mole of a gas would occupy a larger molar volume. Think about a balloon. If it's a hot day, the balloon sometimes pops randomly. This is because when heated, the spaces between the gas particles in the balloon expand until the balloon can expand no more, and bang, the balloon bursts. In terms of pressure, if a gas is in a sealed container and is put under a higher pressure than the atmosphere, then it occupies a smaller volume. If you squeeze an empty soft drinks bottle with a lid on, it proves this idea. When the bottle is squeezed and then released, the plastic bottle usually returns to its original shape. So, in summary, 1 mole of any gas is always approximately 22.4 litres per mole when measured at standard temperature and pressure, or is more usually quoted as 24 litres per mole when measured at room temperature and pressure.
So that's the gist of where we're going with these gases here. 1 mole of any gas at STP will have a volume of 22.4. So how does this affect my stoichiometry, or how does this allow me to do something stoichiometrically with equations involving gases? Well, I want to kind of bounce back and look at, this was our old stoichiometry map where we went to grams to moles to moles to grams. Now with this concept of what is known the molar volume of a gas, we have this possibility right here, okay? You're like, oh my gosh, what is all the spider nonsense here? Okay, we're going to eventually create a lot of possible arms of where we can come from and where we can go to with stoichiometry. One thing we are keeping in mind is that middle part, that mole ratio, that funnel effect that nobody passes through to the other side without those coefficients of the mole ratio, okay? And in fact, I think I'm going to bounce down to the document camera so I can like use my hands on my map. So I always super duper like to use my greens. So everybody on this side of my dotted line is about my given substance in the chemical reaction. And everybody over here with the red line is about my ending substance in my chemical reaction. Okay, so okay, so we did grams to moles to moles to grams. We have done that before. We know this first step would be using the molar mass of my given substance, that decimal number from the periodic table. Then the mole ratio between the two substances, or the coefficients between them, and then finally the molar mass of the ending substance, okay? But now I've given you these guys. If I give you as a given information the liters or the volume of a gas under STP conditions, I can use this as a conversion factor, my molar volume. That just says that 1 mole of that gas will have a volume of 22.4. That is great. I can use that volume to convert me to moles. And then bam, I am ready to open up that door for that funnel effect to go through my mole ratio and go wherever I need to go on the other side. So we've got some kind of options here. I can go from grams to moles to moles to grams. I can go from grams to moles to moles to, I can ask you to take it to liters, or the volume, using the molar volume there. I can go from liters to moles to grams, and watch this. If I give you the liters of a gas at STP and I ask for, well, how many liters of another gas from that chemical equation would occupy that space, I can bypass that step. You're like, well, it's a 3-step process. Well, the reason why I can bypass that and just use a 1-step mole ratio step is, if you'll notice, and we'll get to a problem where we will actually map this out and you will see how this works out. But that mole ratio actually ends up becoming a volume ratio. So the coefficients can represent the ratio of relative volumes of two gases to each other. So we're going to write volume ratio. Okay. Yes. So, all right. I think we are ready to go. I'm super excited. Okay, we have, I think, 3 different sections of possibilities that we're going to do, with one provided notes example, and then on your separate gas volume stoichiometry handout, we'll bounce over here and do a couple of selected problems for each one that I give y'all a notes focused section on. So here we go. So it says, the first section is how to do mass or grams to volume in liters. Okay, it's a 3-step problem. And in fact, if I want to look up here, if I wanted to do grams to liters, yes, that is 3 steps. The first step is the molar mass of that given substance. The second step is my mole ratio, right? And then the third step is my molar volume, my 22.4 being equal to 1 mole of any gas at STP. So that's a 3-step process. But the key thing here is you've got to make sure that you have a balanced chemical equation. That is always step number 1. Then converting the mass of my given to moles using the molar mass, converting the moles of my given to moles of my ending using the mole ratio, and then finally converting my moles into liters of my ending substance with this. Okay, so let's get started. I just talked a lot of words. Okay, I've got my red and my green. I'm ready to go. You know how I love the colors. It really, really helps me out. Okay, it says how many liters of oxygen, but words, I see an equation that it needs to be balanced. So how about we balance that first before we move on? Okay, so let's see. It looks like I got 2 oxygens on the reactant side and I only have 1 on the product side. So let's fix that right away by putting a 2 there. And now with that 2 in front of iron 2 oxide, I need to fix iron by putting a 2 here. Now, if you'll notice in this chemical equation, I put the states or the phases of matter in parentheses behind the specific reactants and products. And the reason why I did that for this specific lesson is because we are strictly focusing on gas volumes here. So you'll notice that in all the problems we're going to be working, when I mention things like liters, whether it's a given value or an ending value, it'll always be represented for a gas and a gas only. And we are assuming that all of these problems are done under standard temperature and pressure or STP conditions. Okay, once again, lots of words. Okay, how many liters of oxygen gas are necessary to produce 100 grams of iron 2 oxide? Okay, I have seen the number in my problem. I'm going to circle it with my green because this is my given. This means go. I'm also circling the units behind it because that lets me know that I'm starting at grams. I ain't starting here. I ain't starting here. I'm starting at grams, okay? So I'm like, amazing. So my grams, my 100 grams of iron 2 oxide, I'm going to find iron 2 oxide. There he is in my problem. And I always write my given underneath my substance that I've given you that information about. Not only the number, but the units. That is important, right? I also like to go ahead and circle that coefficient in front of that guy because that is what I know I'm going to use when I get ready for that funnel effect of applying my mole ratio, okay? Now we're going to figure out what we solve for. Oh, I always tend to underline in my question of what. That helps me find my substance in the chemical equation a little bit easier. Okay, so then we are trying to figure out what I'm asking you to solve for. How many liters? Okay, liters of oxygen gas. Well, hopefully I'm asking you to do liters of gas. It is oxygen gas because this lesson is only liters for gases. So I'm finding oxygen. There he is. I'm going to write underneath him a question mark letting me know that that is who I'm trying to find information about. And which information am I trying to find? His liters. So that lets me know in my process, I am ending right here at liters of a gas at STP, not at grams of that oxygen, not at moles of oxygen, which could be possibilities of questions I could ask you. But for this specific question, I am taking it from grams of my given 2 moles to liters of that gas at STP. Okay, so this is totally going to be a 3-step process. So I'm going to map it out, right? And we are ready to go. I think I need to scoot this back. Okay, perfect. So my process here is this is going to be first my molar mass step. This is going to be my mole ratio step, my coefficients, which I did not circle from my ending substance. And then finally, this last step, we're going to get to use our molar volume of a gas, our 22.4 for the first time, which is really fun and cool. Okay, so I'm going to use my green, and I'm going to start writing my given information in green to let me know that I'm not ready to cross the double line yet until I get through my mole ratio. So my first substance is that iron 2 oxide. My given was 100 grams. 100 grams of iron 2 oxide, yes? And y'all are like, why is there a decimal there? That will be important with sig figs. Y'all are probably also asking me, why is she saying iron 2 oxide? I do not see a 2 in that formula. Well, I'm saying iron 2 oxide because that is the charge of that specific iron. It has to have a charge of a +2, hence iron 2 oxide, to balance out that oxygen's known charge of a -2. I've got a +2 and a -2. That is a 1-to-1 ratio of the charges, which is why you see one of each. That was a tangent, but it was a good conversation on our nomenclature, meaning naming things. Okay, so that is what my given is, right? Now I'm ready to apply the molar mass of this iron 2 oxide. I hope you have your calculator out ready to go. Let's see, my iron's molar mass is 55.85. 55.85, right? And there's only one of him in that formula, right? And then my next guy is oxygen, so I'm ready for oxygen. Let's see what oxygen's molar mass is. It's 16 plus 6, plus 16, there we go. And how many oxygens do I have? I just have one. So this will give me the correct molar mass of my iron 2 oxide. So I hit enter and I'm excited. 71.85. That means there's 71.85 grams of iron 2 oxide in every 1 mole of iron 2 oxide. So I'm going to write that here on paper. I'm going to be writing the 71.85 grams part on the bottom, and then the 1 mole on the top, because the purpose of this is for me to get through that conversion. Me canceling off like units on top and on bottom means that I have effectively done this step and gotten to now moles of iron 2 oxide. Okay, I'm still writing things in green because I'm still talking about my given substance here. Okay, so now we are at moles, and you get excited when you get to your givens moles in stoichiometry because you are ready for that mole ratio. You are ready to grab those coefficients, meaning that this represents there are 2 moles of iron 2 oxide for every 1 mole of oxygen here. I'm going to be writing the 2 moles of iron 2 oxide on the bottom and the 1 mole of oxygen on the top because I want to be able to do that and that. Okay, if it was flippity floppity the wrong way, I would not be able to cancel out like units on top and on bottom. So now you guys, congratulations. We have made it to we've crossed the line. We are at moles of my ending substance oxygen, but we wanted to take it to, where did we want it to go? That's the best part about writing it underneath the chemical equation, is that you may get lost, which I get lost a lot. This grounds me so much. And in fact, once I write this stuff actually underneath the chemical equation, I don't even care about the words on the problem. I know where I'm starting. I know where I'm trying to get to. So it is a super, super useful technique that I have been using for a long time, and I've been doing stoichiometry for a long time, and I get right answers. So I'm just saying, it works. Okay, so I now know I'm going to liters, because you're probably getting excited, like, it's molar mass time for this guy. No, we're going to liters. Well, at STP, we know that 1 mole of any gas is equal to 22.4 liters. So I can say, because we are at STP, 1 mole of that oxygen gas has a volume of 22.4 liters of oxygen gas. Once again, I'm specifying of who for my given. Okay, and then boom, boom. Yes, so this looks amazing. Once again, with this stoichiometry, what I love using the reds and the greens for is you can visually see where you start crossing over that dotted line to start talking about your ending substance. Noticing that that guy right there is the mole ratio. He is the funnel that is required for everything. Okay, so now I'm ready to grab my calculator. I'm super excited. Here we go. Let's see. Our first thing that we need to do, you cannot see. Okay, we got 100 times 22.4. And then I have to divide by 71.85, right? And divide by 2. All right, there's my answer. Okay, I'm going to write down a little bit of this answer so we can kind of do the sig figs of it all, because the rounding is definitely important too. So we get like 15.588. I'm going to stop there. Okay, now our sig figs are going to depend on what my givens value is. So looking at my given, oh my gosh, y'all, look at that given. How many sig figs are there? It is 3. Those trailing zeros are important because there's a decimal in the number, which means over here on my ending guy, my answer, I want that first sig fig. I want that second sig fig. I want that third sig fig. And that is all I want. Everything else goes away. But that last guy, that 8 directly behind that 5, tells me I need to round that 5 up. So what I have here is a 15.6. And you were like, 15.6, what, monkeys? I don't know, what, pencils? No, it's the thing that you did not cross off. So all of this work here that you've done with labeling, with units, and of what helps you out, not only to figure out which way you're orienting your conversion factors, but also when you get to your final answer, there's no question. You're like, oh yes, that is liters of oxygen. Amazing. Cool. Okay. So now it says, now try problems number 1 and 2, which means we're going to switch over to our practice problems on our practice assignment. And hopefully I will not like lose all the things I'm trying to jumble around. I've got calculator, periodic table, practice pages, all of that fun stuff. Is a lot going on here. Okay, so my first problem, there's some words on there, and I do not care about these words because I see a chemical equation that I'm like, oh my gosh, you guys, I've got to balance this chemical equation. So you're like, okay, calcium's balanced. Hydrogen's balanced. Oxygen, we balance, guys. That is great, but please do not forget to check. Sometimes it conveniently is already ones for every single coefficient, but we always need to check because we know how important that is. Okay, so now I'm ready to figure out what they gave me and what I'm trying to solve for, which is super important. So it says, what volume of hydrogen gas will be produced if 28 grams of water reacts with excess calcium? So my given is 28 grams of who? Of water, right? Now, here's my water, so I'm going to write underneath him my given information, 28 grams. I also like to kind of circle because I know that that coefficient of a 1 is going to help me when I get to that mole ratio step. So I'm starting at grams, okay? Starting at grams. Now, where am I trying to ask you to solve for? What volume? Volume. What is volume? Volume is, what are the units for volume? Liters. So if you get confused and they say volume, we're just going to liters. So we're ending off right here at liters of a gas at STP. Of who? What kind of gas? Oh, the hydrogen gas. Where is the hydrogen gas? Here he is right here. So I'm going to write question mark because that's where I'm trying to get to. And the units for volume are liters for this. Okay, amazing. So we know this is going to take me 3 steps. And if you get into a stoichiometry problem and you're like, I don't know how many steps this takes, and honestly, you will get to a point to where you're like, the steps does not matter. I know how to let my units walk me through to end up where I am. So let's just practice that mentality right now, and we will see that it does work out to be 3 steps. But I do know that I always start with my given right there. So my given is 28 grams of who? Water. Okay. So I'm like, well, I got to get out of grams. Well, the way you get out of grams is, well, I got to get to moles. Got to get to that funnel effect of the mole ratio, right? Well, that's going to be using my molar mass of water, right? So I need that certain molar mass of water for every 1 mole of water. So that's my first step. I left that blank because molar mass always requires you grabbing your periodic table and finding all this stuff. So in water, I have 2 hydrogens, which is 1.01, and 1 oxygen, which is 16. So I'm like, amazing. And you know you've reached true nerd status when you kind of start memorizing some of these molar masses. Like, I always know the answer to what water is. It is always 18.02. You're like, wow, that's really nerdy. And it is, and I'm proud of it. So I have 18.02 grams of water in every 1 mole of water. And I cross off as I go along because that's my mental tracking to be like, okay, now I am here. I'm at moles. You get to moles of your given, you are excited, you are ready for mole ratio time, which are the 2 coefficients in front of the 2 substances that you are bouncing back and forth between. Okay, so that means I have 1 mole of water for every 1 mole of hydrogen. Yes, and I've changed colors because using my mole ratio means I've hopped across that dotted line. Now I'm finally talking about my ending substance crossing off as I go along. And am I stopping there? I have forgotten. No, I have not, because I've taken the time to write my unknown here underneath of who. I'm not stopping at moles. I'm taking it to liters. Moles to liters, moles to liters, moles to liters. Oh yes, the 22.4 liters will always be equal to 1 mole of a gas, right? So I'm ready for that molar volume. We say, yay, 1 mole of hydrogen will be equal to 22.4 liters of hydrogen. Yes, putting the mole of hydrogen on the bottom so I can cancel it off. Noticing the one thing that I did not cancel off is my liters of hydrogen, which is good. That's what I wanted to end up. So now I'm ready to calculate. With my calculator, I have 28 times 22.4. Yep. And then I'm dividing it by the only thing of interest, meaning the only thing that is not a 1 on the bottom is my molar mass of 18.02. Cool. So I get 34.80. How many sig figs am I going to round this answer to? My given sig figs is 2. There are 2 significant figures in 28. So for my answer, my calculator, I want the 3, I want the 4, but I do have to round that 4 up to a 5. So my answer is 35 liters of hydrogen. Cool. All right, we've got one more practice for this next type of a problem before we bounce back to our notes. So let's see. Y'all, they did not give me a chemical equation. Okay, so I got to switch my brain. We're not doing stoichiometry. We are desperately trying to read these words to interpret what are the reactants. At least give me the reactants. If I give you at least the reactants, you should be able to use your knowledge of my 5 types of chemical reactions and how to predict the products for those types to construct the products. Okay, let's see. Potassium chlorate decomposes to produce potassium chloride and oxygen. Okay, I've told you some things. Potassium chlorate decomposes. That means he's your only reactant here. So I can go ahead and write him right now. So potassium chlorate is made up of potassium. Potassium is a group 1 alkali metal who has a +1 charge. And chlorate is a polyatomic ion. Which chlorate is that? It is ClO3 with a -1 charge, right? So my formula for potassium chlorate is KClO3. I have a 1-to-1 ratio of each one of those things. You can keep parentheses around your polyatomic ion. It is not necessary because there's only 1 of him. If potassium had a charge bigger than a +1, that would require the parentheses because you would need more than 1 of that chlorate ion to neutralize that ionic compound. Okay, so it decomposes. It decomposes to produce who? Potassium chloride. Okay, so let's focus on the potassium chloride of it all. It's made of potassium and chlorine. Whenever I see IDE ending, it typically means a single element off the periodic table. Chlorine's got a -1 charge, right? So I have a +1 here and I've got a -1 here. So the formula for potassium chloride is just KCl. And once again, guys, if there were more interesting subscripts over here, let's say that potassium had a 2 underneath him, when we write our products, we always ignore whatever baggage from that previous single life relationship here. We've got to make sure that we drop the subscripts and create our own formulas from scratch, okay, based on the charges of the compounds. Okay, so potassium chloride and oxygen. Like, woo, single oxygen. I know he came with a 3 here. Ignore that. That is a previous subscript from his old life. He is now new. He's just oxygen. Unless he's one of my Hofbrinkels, my diatomic elements, right? So he gets a 2 because he is. He is hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those are your 7 diatomic elements. They are the only ones when you write them single who get a 2 subscript. Everybody else get no subscript. That was a lot of talking, but I am taking the time to review how we write our chemical equations because it is hard, and I have a feeling if you're watching this video, you are probably needing some help in some way, and I'm here to help. Okay, so I've written my equation. Now I am ready to balance it, hopefully. I've got 3 oxygens on this side and 2. I love my rule that says a 3 to 2. I'm going to double on the 3 side. That typically gets me started. Okay, that does mean I need to put a 2 in front of my potassium chloride, and it does mean I need to put to make 6 oxygens, you need to put a 3 in front of that oxygen. We had to do all of that work, and I did not even look at the numbers, what they gave me, what they're asking me to solve for. So now I finally get to do that. All right, I got my reds and greens. Okay, how many liters of oxygen gas are produced? Here's my given, 100 grams of potassium chlorate. Okay, my given is of this guy, potassium chlorate, and I have 100 grams of him. Cool, that's where I'm starting. Maybe I'll circle my number, my coefficient for the mole ratio. And then what am I trying to solve for? How many liters of oxygen? Well, who's oxygen? That guy right there. So we're going to write question mark liters, okay? So we're going from grams to moles to moles to liters of that gas under standard temperature and pressure. Let's see if we can let our units do the walking and talking to tell us how we would get this as 3 steps. Okay, so we are ready. My given is right there. I'm excited. Here we go. 100 grams. And my of what is KClO3. Grams here, need to see grams here, right? I can't change my colors because I have not gotten to moles of my starting substance, have not gotten to moles of my potassium chlorate. Okay, you're like, okay, grams to get to moles, molar mass time, which means I will have to check my periodic table and add up all of those guys, which will represent how many grams are in 1 mole of that guy. The purpose for this is to go bam, bam, and get me to moles. We are there. We are ready to open the door to get to the other side of the stoichiometry map by using the mole ratio on the next step. But first, let's go ahead and do our molar mass. Yes? So potassium, and I'm not going to keep bringing my periodic table. I may do a few times, but just do not be confused when I'm doing molar mass and you're like, why is she typing these numbers? I'm grabbing them from the elements, decimal numbers from the periodic table. Okay, so potassium's is 39.1. Okay, and there is only 1 potassium in that formula. And then chlorine's is 35.45. And there's only 1 chlorine. And then oxygen's is 16. And there are 3 oxygens. So the formula, or the molar mass for potassium chlorate, is 122.55. So I'm going to use my green. 122.55. They're 122.55 grams in every 1 mole. Okay, boom. I'm at moles of my given. Amazing. We are ready for the mole ratio. Yes. Which means I'm going to look at my coefficients between my given and my ending guy. Okay, so that lets me know that for every 2 moles of potassium chlorate, I have 3 moles of oxygen gas. Yes? And then I'm like, boom, I have crossed over to the dotted line. I don't know, all about oxygen. Well, what do I need to find about oxygen? Surely not stopping at moles. I said I needed to take it to liters. Moles to liters of a gas, 22.4. We are ready for that molar volume. So, in every 1 mole of any gas, this time oxygen gas, there will be a volume of 22.4 liters. Yes? So doing this means I get away from moles. I have now made it to liters of that oxygen gas by using that 22.4. Okay, so we know that when we get our calculator and we start typing things in, we will get our answer, which is really exciting. So I have 100 times 3 times 22.4 equals that. And then I'm going to divide by anything of interest on the bottom, divided by 122.55, and divide by 2. Okay, so they're going to be 27.4-ish and some change liters of this oxygen gas. But how many sig figs am I looking at here? So in my problem, that's got 3 sig figs. That decimal makes those zeros important. So I need to write down 3 significant figures from my calculator. That means I'm going to be writing down 27.4, and I do not need to round that 4 up. So the units finally are liters of oxygen. Oh, I love it. Look at that. That is good stuff right there. Okay, so that's our first type of problem where we started at grams of our given substance and we took it all the way to liters of our ending substance under these STP conditions. Okay, so now we're going to bounce back to our notes page and we're going to flip to the back. Yes. Now this one, we're going to do a section on how to do volume or liters of a gas to mass of something else. That's also a 3-step process, because if I start you out here, you still got to take it to moles from that liters, and then you take it to the moles of the other guy, and then you're going to take it to grams of the other guy. So we'll be using the molar volume first, that 22.4, then my mole ratio, my coefficients, and then finally my molar mass, but of the ending substance this time. So it is a 3-step process. First thing we got to do is make sure we go balance, right? So for balancing this, we got hydrogen plus oxygen comes together to make water is my chemical equation for this one. So glaringly obvious here, I've got 2 oxygens here and only 1 on this side. So I've got to fix my oxygens by putting a 2 in front of my water, which then means I need to somehow get 4 hydrogens on this side like the 4 I have here. So I will put a 2 there. All right, so we're balanced. Now we're ready to read the problem. You're like, what is she asking me to do today? How many grams of water will be produced? I zone in on that number. Boom, given. That is important to me. 300 liters of hydrogen gas. Where's hydrogen? Where's hydrogen? There he is. So I'm going to be writing 300 liters. Notice that there is no decimal behind those zeros. I know we had seen that, I think in a couple of our examples. That is going to change the significant figures, which we will talk about here in the end when we get the problems answered to even look at. So we have our given of 300 liters of the hydrogen gas. I took the time to go ahead and circle my mole ratio because I know I'm going to need it when I cross the dividing line. Okay, what are we asking me to solve for? Grams of water. There's water. I'm going to question mark grams and circle my guy. So now the words of the problem do not mean anything to me. I know immediately I'm starting at liters of hydrogen and I'm taking it to grams of my water, okay? We said this was a 3-step process. I always feel like I'm bad at estimating how much space each one of these steps are going to be. So we will see. We will see how successful I am this time. Okay, so my given is going to start here, right? And the first step is using the molar volume of that gas. And then this next step is the mole ratio between the 2 substances. And then finally, the last step will be the molar mass of my ending substance. So my given is 300 liters of H2. That was terrible spacing, but whatever, it's fine. Which means I need liters down here, right? I was like, oh, okay, well, now I've forgotten. Well, the purpose of this next step is to eventually get you to moles, right? I gotta get to moles. This first step is always getting me to moles. Well, what do I know that relates liters of a gas at STP to moles? Oh, yeah, in every 1 mole, 22.4 liters. You see how I kind of did that with my brain? Sometimes it's good to use our brain as opposed to be like, what do I do? Map, tell me what to do. Yes, my units, I really kind of like to have my units plan me out. Okay, so that means I'm out of liters of hydrogen. I'm at moles. Yay, I'm moles. I'm ready for the mole ratio. I already have them circled right there. It is a 2-to-2 ratio, which means for every 2 moles of hydrogen, there are 2 moles of water. Amazing. So the purpose of that step is now, I've crossed over the dividing line, but I do not want to start or stop at moles of my water. I wanted to take it to where? I've forgotten. No, you have not because you've written it here. Oh, grams. Okay, I got to go from moles to grams. So that means I need moles here of H2O. And if I'm going to grams, I need grams here up at the top. You're like, what is the thing that relates grams to moles? Oh, yeah, it's the molar mass, which means some decimal number from the periodic table is going to tell me however many grams I have in 1 mole. We've done the molar mass for water before. I will show it again, but I won't use my periodic table. 1.01 is the molar mass for hydrogen times 2, and then plus 16 for the oxygen. It is still 18.02, which is good. It's nice that things have not changed in the past 10 minutes. Okay, so I've done that. I'm super excited because now I'm out of moles. I have made it to my grams. So what we've done here is we've gone from liters of our given guy to moles of our given guy. And then we've gone from moles of our given guy to moles of our ending guy. And then finally, we took it to grams of our ending guy up here. So just to kind of track us in there. Okay, so now we're ready to do our math and calculate. We have got 300 times 2 times 18.02 equals, and we're going to divide by 22.4 and then divide that by 2. Amazing. So that is my answer. I'm like super excited. I'm going to go ahead and write out a few of these numbers because I want us to have it on our page for us to kind of manipulate when we round to a certain number of sig figs here. Okay, 7-ish. Okay, so you're looking at this, and you guys, how many sig figs are in that number? It is not 3. Those trailing zeros are not significant because there is not a decimal in that number. So that means, how many sig figs do you have? Just 1 sig fig. So when I get to my answer over here, I just want that 2. That is it. Do I need to round that 2 up? No, the 4 tells me you do not have to do that. But my answer is not 2. I need to make sure that 2, which is in the hundreds place, stays in the hundreds place by putting some zeros. And once again, those zeros are not significant because there's not a decimal in the number, just like what my given information showed me. What are the units for my answer? You know, because you didn't cross them off. It's grams of H2O. Wonderful. Okay, so now it says, now try problems 3 and 4. So we're going to get back out our practice page, and we're going to try problems 3 and 4. And it says these are our volume to mass problems, the example problems that we just did by going from volume of a gas at STP to mass of another substance. Okay. So it says, first of all, I need to balance a reaction equation, right? So I got this guy, I got carbon disulfide and oxygen, and turns into carbon dioxide and sulfur dioxide. So all of these are covalent compounds, which is why I'm using the word di to represent how many of each I need. So I'm looking here, I'm like 2 balanced, 2 balanced, 2 balanced. It looks like, who was not balanced? I got sulfur's 2 over here and sulfur's 1 over here. So how about we start off by doing this, right? And then that changes my oxygens. Looks like I have 2 oxygens on the reactant side, and let's count up all of the oxygens on the product side. 2 coming from the carbon dioxide and 4 coming from my sulfur dioxide. So this is 6 total oxygens on the product side, which means to make 6 over here, I put a 3 right there. That was a fun one to balance. I actually really like that. Okay, so now we are balanced. Now we are ready to read the problem. It says, in the reaction below, how many grams of carbon disulfide are needed to produce 500 liters of carbon dioxide? So my given with my number is 500 liters of who? Carbon dioxide. So carbon dioxide is right here. We are starting with 500 liters. And his coefficient up there in front of him is a 1. That's where we're starting. Where are we trying to get to? Grams. Grams of who? Carbon disulfide. Where's carbon disulfide? He's right there. So we're going to him. So we're going to question mark, and we're going to who of him? Grams. Okay. Also has a coefficient of 1. This is going to be fun. Okay. So we may not know that how many steps it is, but we're going to let our units do the talking and help us through this stoichiometry problem. My giving goes first. 500 liters of who? Carbon dioxide. Which means I need liters of, well, that looks like LCO. You guys get it. Liters of carbon dioxide on the bottom. The purpose of this is to get me to moles. Remember, we always need to get to moles, right? Well, how am I going to go from liters to moles? If this is a gas at STP, then we know there are 22.4 liters in every 1 mole, right? Cool. So that makes sure that I cancel off. I am now at moles of my given, which means I'm getting excited because I'm ready to implement my mole ratio, the coefficients, which since there's 1s in front of them, it is a 1-to-1 ratio between carbon dioxide and carbon disulfide, right? Which means, boom, I'm now effectively cross that dotted line. I'm now at moles of my ending substance. Well, what am I taking it to? Grams of my ending substance, which means to take this from moles to grams. How am I going to do that? How am I going to relate moles to grams of something? By its molar mass, which means in every 1 mole of this carbon disulfide, there's a certain amount of grams. So that means I grab my periodic table. I say, okay, periodic table, tell me what's going on here. Well, carbon's molar mass is 12.01, and there's 1 of them. And then sulfur's molar mass, I have to double check, oh my gosh, 32.07. And there are how many sulfurs? 2. Okay, so my molar mass of carbon disulfide is 76.15 grams in every 1 mole. So I've done that. I feel good. I'm like, okay, great. That looks all good to me because now I can cancel off moles of carbon disulfide on top and on bottom. So now I'm ready to calculate what my final answer will be. I have 500 times 76.15. And then dividing by 22.4. And that is all that I need to divide by. Okay, so my answer, I'm looking at this fun thing, and I'm like getting excited. I'm like, woo, 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 woo. Okay, how many sig figs? Oh, this is a good one. I'm very excited about that. How many sig figs are in your given here? 3. I'm like, great, I can round this to 3. This sounds good to me. I'm like, okay, here we go. So I want that 1. I want that 6. I want that 9, and that's the last one I want, but y'all, I got to round that 9 up. In fact, I'm gonna write some of this stuff. Ish. I got to round that 9 up, right? That 9 up because this 9 is bigger than 1, right? So I'm looking at rounding that 9 up, which means it turns into a 10. Y'all, I'm dealing with 1, 7, 0, 0, right? But how do I make that be expressed in 3 sig figs? How do I let you know that, well, I want that 0 to count, but not that 0? You can express this number in scientific notation, okay? If I express it in scientific notation, it would be 1.7, and I can put that one significant 0 that I want. And that would be 1.70 times 10 to the what? Third. Ooh, that was a sneaky one. That's a 3. Sorry, you guys. And what are the units for this? Grams. And of who? Carbon disulfide. So here's my answer. That was a sneaky sig fig problem, but those are always fun to get sometimes. Okay. Now we are ready for the next one. There is no chemical equation to be found. I've got to figure out what it is I'm dealing with here. Please, what are my reactants at least? Nitrogen and hydrogen combine to produce ammonia. They are literally telling me everything that is in that reaction equation. I'm very excited about that. So nitrogen gas is my first thing. Plain old single nitrogen. Single, yay. But he's one of my diatomics. He's one of my Hofbrinkels. So he always comes in twos. My second reactant is hydrogen. Hydrogen is also a diatomic. He is the first letter representative in my Hofbrinkels. So they combine to produce ammonia. Ammonia is one of these substances similar to water that everybody in chemistry at least knows what the ammonia is. Ammonia is always NH3. And if you didn't know that, you're like, oh my gosh, how am I supposed to know? We will use it enough to where it is, you will have it committed to memory very, very quickly. Okay, so now I need to balance, right? So for balancing this, it looks like I have hydrogens and nitrogens being both an issue. Let's start with nitrogen. I got 2 over here and 1 over there, so I'm going to put a 2 in front of ammonia. And now I've got 6 hydrogens here, so I need to get 6 here, so I'm going to put 3 here, right? That 3 goes right there. I'm really excited. We are ready to now figure out what we're starting with and what we're trying to get to. There's my number. So we're starting at 130 liters of who? Nitrogen. Here's nitrogen. 130 liters, which is very exciting. I know I will need that for my mole ratio. Where am I trying to get to? Grams of who? Ammonia. Here's ammonia. So I'm going to ammonia, question mark, grams. All right, let's see. So we're getting ready. We have, I may make that a little bit longer on this end since these problems take up a lot of space. So I have 130 liters of nitrogen. We're starting at liters, which means I need liters on the bottom to get to moles. It is the molar volume of 22.4 liters is equal to 1 mole of N2. So we've done that. That gets us from here to here, which means my next step is to use my mole ratio, which are the coefficients between those two guys, right? So we know that 1 mole of nitrogen, there will be 2 moles of ammonia that will be produced. So now I can cancel out. I've crossed over. I'm talking about my ending guy, but did I want you to tell me how many moles of my ending guy? I did not. How many grams? So I'm going to take that moles, 2 grams, by using the molar mass, which states for every 1 mole of ammonia, there's a certain amount of grams of ammonia. According to my periodic table, I find nitrogen. That decimal number next to nitrogen is 14.01. 14.01. There's one of him. And then my next guy is hydrogen, 1.01 times 3 of him. The molar mass of ammonia is 17.04 grams in every 1 mole. So the purpose of doing this is now I can cancel off. The only thing I've not canceled off is what I'm solving for, grams of ammonia. Yeah, that looks good to me. So now we are ready to math it up. 130 times 2 times 17.04. And I divide by my molar volume of 22.4. And my answer is 197.78. Okay, sounds good to me. I'm going to write a little bit of this number down because I think this is another fun one. Oh, this is another fun one. Okay, so I have 197.78. We'll leave it there, okay? How many sig figs do I have in this number? Oh, that's 2, which means I need this guy and this guy. Nobody else is of interest to me. So I've got to round that 9 up just like we did last time, because look at this guy causing an issue right here. Well, if I round that 9 up, it becomes a 10 to where that guy then spills over, which means I have 200. But how do I let you know I want 2 sig figs from this number? Scientific notation. This would be 2.0 times 10 to the second. And the units for this guy are grams, right, of who? Ammonia. Ooh, that's a 3. Look at that. That was a good, these little problems were good kind of reminders of our scientific notation being helpful with sig figs. All right, we're going to bounce back to the notes, and we're going to do the very, very last type of problem. Oh, these are good. The very, very last type of problem that you can see with these volume of gas problems, as long as the gases are at STP. So this is a volume to volume type of a problem. So if I give you a starting amount at liters and I ask you to find a starting amount at liters, you guys, it actually is 1 step and 1 step only. You can do a 3-step process. That sounds good. That is an option for you. And in fact, I think when we do our first example, we will do the 3-step problems. And I'm going to show you when you have it written down, oh, this is maybe why I can just bypass everything here and go to that volume of the mole ratio here, right? Okay. So let's go ahead and get started. Balanced chemical equation, balanced chemical equation. We are not balanced. It is the same chemical equation as our first example. It is the formation of water from hydrogen and oxygen. To balance, I put a 2 in front of oxygen. Oh wait, no, I do not put a 2 in front of oxygen. I need to put a 2 in front of the water to give me 2 oxygens. And then I put the 2 in front of hydrogen. Okay, my given is the number in the problem. I have 49.0 liters of who? Oxygen. I'm starting there, 49.0 liters. I will be using that number of a 1, not a 2 like I tried to do before, and as the coefficient for that mole ratio. And then my ending substance is how many liters? So I'm asking you to take it to liters of the water vapor gas, right? Because I can only take things to liters right now for gaseous reactants or products. Okay, so I'm like, okay, I'm starting at 49.0 liters. I will be showing and modeling the full transition of liters to moles to moles to liters, okay? Because I think that this will do a good job of proving our point on why we were able to do this as only 1 step. Okay. Set up 3 spaces. My given goes right here. So I've got 49.0 liters of who? Oxygen, so O2, which means I need liters down here. And the purpose of this is to take it to moles, right? Molar volume. We know there are 22.4 liters in every 1 mole. So that gets me to moles, which we are very excited because we are now ready to use the coefficients for the mole ratio between these 2 things, right? So that states that there is 1 mole of oxygen for every 2 moles of water vapor or gaseous water. So now I finally started talking about my water vapor guy. I'm very excited about that. We're taking it to liters though, which you're like, okay, liters, what am I doing for that? Well, I need to leave moles to get to liters. Well, for this gas at STP, we know that 1 mole will always occupy a volume of 22.4 liters, right? So boom, boom. This will totally get you the correct answer, okay? In fact, let's just calculator it up to see what we got going on here. And, you know, we can then look at some things that our calculators may be pointing out to us that we have not thought about. I got 49 times 2 times 22.4. And then I'm going to divide by 22.4. I multiplied by 22.4 and I divided by 22.4. Guys, this is why we're able to do only 1 step. It's because these 2 conversion factors right here, they cancel each other out. Those mathematically, 22.4 and 22.4, are pointless here for us. So what that means is I can now say that this mole ratio is a volume ratio between these two gases, okay? So this would be 2 liters of water is equal to 2 liters of oxygen, which is what we're going to model here when we do the exact same problem down here below. You're like, oh, we're doing it again. It's one step, so calm down. We're fine. We're fine. Okay. So I look at this. I'm like, my given. We're just doing the same thing over and over again. I'm showing you how we can do this in one step. My given was 49.0 liters of oxygen, right? And I know I'm taking it to liters. I get so excited when I see liters to liters of 2 gases at STP, which means I just take those numbers and I'm like, boom, that's now a volume ratio, which tells me that there is 1 liter of this oxygen gas at STP for every 2 liters of that water gas, right? So look at this, you guys. Boom, boom, so fast. And we said that we were basically getting rid of these 2 steps. That is exactly what we're doing here. So mathematically, that's what I got. I got 98 when I did all this stuff. Let's see if we also get 98 when I got rid of those steps that I said were not important mathematically. 49 times 2. Yeah, 98. Well, how many sig figs do I need to round my answer to? This answer is 3 sig figs, or this given is 3 sig figs. Well, they only gave me 2 numbers. That is fine. You can add a 3rd sig fig. Let me show you how that works. 98.0. That gives me 3. And the units are liters of water. Cool, 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 cool. Okay, yes. All right, now we are ready to do our remaining 2 practice problems from our practice worksheet assignment. It says now try problems number 5 and 6. We will try problems number 5 and 6. That sounds like a great idea for us, right? Okay, that's on the back page. Hold on. Here we go. Okay, so here's problem number 5. We are now doing volume to volume problems, okay? It says, oh, first of all, chemical equation. I have one, but is it balanced? No. This one's a fun one to balance, okay? So I have phosphorus and hydrogen creating phosphorus trihydride here. So it looks like my hydrogens are going to be the issues. Also, my phosphoruses are the issues. I got 4 here. Let's maybe put a 4 in front of phosphorus trihydride. Or there's another name for it. Apparently, it's called phosphine gas. Today I learned. Okay, so now that changes the number of hydrogens. I got 12 over here on the product side. To get 12 hydrogens on the reaction side, I got to put what do I got to put? A 6. Oh, that's fun. I like this. So now we're balanced. Now we zone in. Where is the number in the problem that represents my given? I'm starting off with 0.42 liters of hydrogen. Underneath hydrogen, I write my given of 0.42 of what liters, right? That means I get to use that cool coefficient of 6. That's not very common that we get to use a big number like that. So I'm already excited about this problem. Determine the volume. And if they had not said in liters in parentheses, we know that volume is liters, right? Of who? Phosphine gas, which is pH 3. So I'm going to go question mark liters for him. And I know I'll use that for. So I'm like, oh, liters to liters of a gas at STP. You may do all 3 steps, but you can use your mole ratio or your volume ratio between these 2 gases. One step. Let's do it, you guys. Okay, here we go. These are always real short problems. It makes me super happy. My given is 0.42 liters of hydrogen, right? We are ready for that mole ratio, volume ratio, which tells me that there are 6 liters of hydrogen gas for every 4 liters of this phosphine gas. Yes, we are just using that mole ratio for these 2 gases at STP because they will have the same volume, right? 1 mole of any gas at STP is equal to 22.4 liters. So if I have the same amount of moles of 2 different gases, they will have the same amount of volume. So we're very excited about that. Okay, so now I grab my calculator. I have some math to do. I have 0.42, right, times 4, and then divided by 6. Okay, so that's my answer. I got 0.28. How many sig figs do I need? Careful. Leading zeros are never important. The only sig figs in this number are the 4 and the 2. So I have 2 sig figs, which means my answer needs to be 2 sig figs. And with that same mentality, cool, that is already 2 sig figs. So my answer is 0.28. The units are liters of who? pH 3. Nice. So that feels good, going liters to liters, one step, just using the mole ratio, not as a mole ratio, but as a volume ratio. Okay, last problem that I think we're going to do together is number 6. There's not a chemical equation, so first thing I've got to tackle is to write my own chemical equation here. Hopefully it's not a very tricky one. I'm excited. It says, how many liters of methane gas? Okay, so methane gas are needed to react with 4 liters of oxygen gas for the combustion reaction at STP. Okay, well, they gave me some reactants here. We got methane gas. They told us it is CH4, and they're reacting with oxygen gas, so plain old oxygen. His symbol is O, but he is diatomic, so he gets a 2. What do I do with this? Do I have something that's a hydrocarbon? And is my other reactant oxygen? I get to do a combustion reaction with that. And y'all, they even told you we're doing combustion reaction equation. But the products for a combustion reaction are always CO2 and H2O. Now when it gets time to balance these, I start with carbon first, balance carbon first, then balance hydrogen next, and leave my oxygen for last. Absolutely. So carbons are balanced, 1 on each side. Hydrogens are not balanced. I have 4 here. I need 4 here, so I put a 2 in front of my water. Now finally I got to balance my oxygens here, right? I've got 2 oxygens from water and 2 oxygens from carbon dioxide. 2 plus 2, I got 4 oxygens on this side, which means I need 4 here, which means I need to put a 2. Wow, that was a lot. Okay, now we're ready to read the problem and do the stoichiometry that is being required of me. Boom, my given, 4 liters, boom, of oxygen gas. There's oxygen, 4.0 liters. There's my coefficient that I've got to use, right? What are they asking me to find? Liters of who? Methane. There's methane. Cool. Question mark liters. There's my coefficient that I will utilize. Liters to liters of a gas at STP. Liters to liters. One step using that ratio of coefficients as a volume ratio. Okay. I've got 4.0 liters of O2. The mole ratio, the volume ratio between these two substances is a 2 liters of O2 to every 1 liter of methane. I have canceled out. I am now at my liters of methane. I have made it all the way over here with only 1 step. Okay, so now I'm ready. Calculator. I bet we could do a lot of this in our head, but I just, like the security of my calculator helping me find answers. 4 divided by 2. Amazing. Okay, my answer is 2, but how many sig figs do I have to write down? I have to write down 2 significant figures. Not a big deal. I can just go 2.0. And my units are liters of CH4, or liters of methane. Awesome. Okay. So we've got lots of options here, guys. We have all certain flavors of options that we can do with stoichiometry. This is as far as our stoichiometry map is going to branch out for this specific unit. That is an intro strictly for the concept of stoichiometry at all. But the key thing is this ding-dang mole ratio. Those coefficients, you guys, are so important. So I cannot stress enough your ability to balance your own chemical equation and feel good about those coefficients, because it affects everything coming down the line. So now we have lots of different options, the type of stoichiometry problems that I can ask you, and each one is just super fun to work at because it makes you feel smart, and we love that.